You're just training. I always talk to you over Zoom.
Oh,
You're my
advising.
advisor.
Yeah, I know. I always because most people don't turn on their camera, so I'm
Yeah,
like, oh,
sometimes I do, but our meetings are usually really first thing in the morning.
oh yeah, yeah.
So
No, that's
my
fair.
camera's usually off.
No worries, no worries.
Yeah.
Hey, what's your name?
Christina?
Christina.
Yeah.
Nice to meet you.
Nice to meet you. I talked to you in the semester.
Right.
Spiders too. Nice.
I'm gonna try. Just
I'm gonna see this
Okay.
and I'll see a picture with that.
Okay, cool.
It should be awesome. Thank you so much.
All right, it's 5:30. Let's go and get started. All right, good afternoon, everyone. How's everyone doing? Good. It's good to hear. Good to see everybody. Okay, so today we're continuing. Hang on, is my audio on? Can you guys hear me on Zoom? Okay, let me see.
Yes, you're good.
Okay, good. Okay. All right, so today we're continuing our I guess you could say introduction to MATLAB, but today we're actually going to be applying it to something. So we are going to be implementing a frame code in MATLAB. So basically, we're going to take everything that we went over on Tuesday and then apply it to a finite element problem here today. Okay. So it's interesting. So we're going to get kind of the bare bones of the code here. I'm going to walk you through everything, so don't worry. I think if this is your first I would say, kind of real problem in MATLAB, I would say this is kind of a big jumping off point. So it's kind of like I'm taking you guys as sledging and just chucking you out of the nest. But I'll be there, so I'll be there to kind of walk you through everything. But you'll see that, hopefully, I think hopefully everyone sees that, even though it may start as something that's very kind of large and intimidating, but by the end of lecture, hopefully that, you kind of feel more comfortable doing stuff like this. Maybe not 100% comfortable, but, more comfortable than when you started. Okay. Okay. So to start, let me do this, right? So if everyone can go to the Canvas website, I've actually posted a starter code for today. So if you go to the page for week 6, you'll see that there's an additional file at the bottom there called frame FEM code _start. Okay. So please download that file and please open up MATLAB. Okay. So I'll be talking, for the first, maybe 10, 15 minutes or so. So, while I'm kind of talking, just make sure that your MATLAB is open and that you do have the starter code open as well. Okay. So if you look at that starter code, you'll see that I have most of the bones of the code there already. And so I actually bring it out here. So I have most of the bones already, but everything that I want you to write, I have as to do. Okay. So, I hope that this is kind of a good way to kind of give you some training wheels on how to implement a finite element code. So, at the end of the day, our code here is going to be over 200 lines long. But most of it, or most of the structure, is there kind of for you already. So you kind of just have to fill in what you need to. Okay. Okay. All right. So while you guys are getting that open, let's go ahead and kind of introduce the topic. But actually first, let's do this. So just to just to kind of be clear with everyone too. So remember, our midterm exam is scheduled for Tuesday, March 10th. Okay. So the date is Tuesday, March 10th. Okay. So that's not next Tuesday, that's the Tuesday after that. Okay. So remember, the midterm exams, those are the only days that I require you guys to be here in person. So please make plans to come. So if you're on Zoom, then if you typically attend on Zoom, then, you need to be in the class on that day. Okay. So the format of the exam is the following. Okay. So on the one hand, there are going to be 4 short answer questions. Right. So the short answer questions are conceptual in nature. Okay. So very similar to the homeworks where, I start every homework, I ask you to answer, some short answer questions. So very much in that same vein. So this is going to be worth about 40% of the points on the exam. Okay. So I do put a large emphasis on the conceptual questions because, honestly, if you take a class like this, you go out into the real world, you may not, maybe in like a month or 2, you're not going to remember the intricacies of how to apply the direct stiffness method for certain elements. But what I hope kind of sticks with you is the conceptual understanding of everything that we learned in the class. So I do put a heavy emphasis on the conceptual information. So please make sure you guys are studying that. Okay. There are going to be 3 problem solving type questions. And then for this part of the class, there's only one type of problem that we've learned, which are direct stiffness problems. Okay. Okay. And so these will be the other 60% of the points. Okay. So you can definitely expect to see some spring problems. You can expect to see some truss problems, some beam problems, 1D, 2D, right? But I'm not going to put any frame problems on the exams. Okay. That's kind of just cruel and unusual. Okay. But you can definitely expect to see 1D, 2D, spring truss beams. Okay. Now, what to study for the exam? Okay. So first off is the homeworks. And so problem set 1 and problem set 2. Okay. So those are probably going to be your best resources to study just because those are kind of fully worked out problems. Okay. So I would definitely work out the problems again. Okay. And And so, when you're studying the homework problems, I always tell students, don't look at the solutions. And that reminded me, I haven't posted the solutions yet. I know I promised you guys I posted solutions, but just the last couple of days have been kind of crazy, so I haven't yet. But I will tomorrow. So tomorrow I will post the solutions for homework 1 and 2. Okay. But when you're using them to study, don't look at the solutions when you're working the problems again. Only look at the solutions after you've worked them out yourself. Okay, that's kind of the best way to study, because that kind of simulates what it's going to be like on the exam. Because on the exam, you're not going to have the solution in front of you, and so it's good practice to kind of go through and try to do the problems on your own. Okay. The other thing I'm going to post is I'm going to post a study guide. Okay. So the study guide will probably go up tomorrow as well. So the study guide is basically just should be just one sheet of paper that kind of outlines kind of everything that we've covered up to this point, conceptual information, problem-solving type information. Basically, it's going to have all the learning objectives that we've gone over so far in the class. So definitely use a study guide to help you study as well. Okay. Okay, and the last thing is what to bring to the exam. It's kind of nice. I usually don't have a computer here to type all this stuff. Usually I write it on the iPad. So for the exam, definitely bring a writing utensil. I generally recommend pencil just because of the nature of these problems, but I've seen just some mad lads use pen for their engineering exam, which is insane to me. But whatever you feel most comfortable with. Okay. Definitely bring a calculator. That's definitely going to help you out because there's a lot of calculations to do on these types of problems. So calculator will help speed that up. Okay. And then you can also have one 8.5 by 11 sheet of notes. Okay. And you can write, and you can use both sides of the sheet. Okay. So your cheat sheet, you can write anything on the cheat sheet. The only thing you can't have on the cheat sheet are the answers to the exams, which I don't know how you would obtain that unless you hack my computer. But you can have, you can write conceptual stuff on there. You can have homework problems on there. You can have problem solutions. I've seen people just take my lecture notes and just print it extremely small on the cheat sheet. You can do that, I guess. I don't think that's very helpful, but that is available to you, I suppose. But yeah, cheat sheet is kind of your own free reign to kind of do yourself. Okay. Now, I do recommend for your cheat sheet that you do actually write it from scratch. Just because the process of kind of taking everything that we've learned over these first 6 weeks and condensing it into a single sheet of notes is actually also a very great study tool. And so what I found is that, when I was taking exams and when I was in college and grad school, that I would spend a lot of time making my cheat sheet and really kind of condensing the information, going over it again, that when it actually came time for the exam, I actually even hardly used the cheat sheet because it's already in my head. Okay. So definitely take the time to write your cheat sheet, and I promise you it's going to be time worth spending on it. Okay. Okay. All right. So this is, I think, everything for the exam. I think anything else I might want to say. Any questions on just the format of the exam or just the date or anything like that? Okay.
For the direct stiffness problems, I know we're going to be working through them, but would the stopping point be solving them for the most part, or would you expect?
Oh, that's a great point. Yeah. So obviously you won't be able to get the solutions to the direct stiffness problems on the exam because there's no computer, so there's no access to MATLAB. I know some calculators can do solutions to differential equations, but not everyone has that. I'm generally working under the assumption that everyone just has a scientific calculator. You can bring your graphing calculators, that's fine, but I know not everyone has one. So for the direct stiffness problems, you would basically stop after applying the boundary conditions. So basically, I'm going to be looking at your final. I'm going to be looking at every step that you did along the process. But the main thing I'm going to be looking at is just the final linear system with the boundary conditions applied.
Yeah. Sounds good. So I guess from the methodology we've learned, steps 1 through 3 only.
Exactly. Yep. Mm-hmm. All right, question. So the homework problems generally took a long time to do. Will the questions on the exam be as time consuming? That's a great point. So this exam, I think people historically on this exam, I think the material, I think people just don't find that challenging, but the challenging thing is going to be the clock. So I will say that the problems on the exam are not going to be as long or as complex as the homeworks. And so I'm not going to give you a problem with like 6 different elements, 7 elements like that. So I'm gonna be limiting it to maybe 2, 3, well, not 2, maybe 3 or 4 elements. But with that said, it is still a lot of writing. And so you definitely want to be mindful of the clock. And definitely, try to do just some little things that help save you some time. So if you have a matrix that has a lot of zeros, don't bother writing all the zeros. I can tell where if you write a matrix and there's blank spaces, I know that means there's a zero there, right? So don't waste time doing, writing stuff because you're going to be strapped on time a little bit, even with the shorter problems. So, try to be as efficient as you can with the time for sure. Is there a question in the class too?
Yeah, so for sure, no frames problems on exam. Right?
Exactly. Yes. Yes. Yeah. So just springs, trusses, and beams.
Okay.
Mhm.
I know like every single problem can vary a little bit.
Mhm.
In terms of the variability, is it going to be extremely like different than what we've done in the homework before, or is it going to be relatively the same, just maybe a couple numbers or like different stuff like that?
So they're all going to be new problems, and so I'm not going to give you the same figure or the same diagram as one of the homework problems,
Okay.
but they're all going to be the same concepts.
Okay.
Mhm. Yeah. So usually on this exam, I'll have one problem that's just purely 1D, and then another problem that's 2D, and then another problem that is a beam with maybe a spring or truss attached. So that's generally what you can kind of expect. So it's the whole gamut, right? So basically, don't put all your eggs in one basket. Definitely study broadly. So my exams, I definitely reward people who study as much as they can, right? So I don't try to favor one. I try to make it as balanced as I can for everything that we've covered. Yeah. Mm-hmm. Question, yes.
Sorry, just the reason why I was asking these questions is that I still don't have the textbooks yet.
Okay. Mm-hmm.
So mainly right now, my main focus, the main thing that I'm kind of trying to study from are the lectures and the homework.
Mhm.
So I guess my question would be, would that be enough, or do I need to go back to the textbook and do other outlets for extra practice?
Yeah, no, I would say the lecture notes and the homeworks definitely give you enough practice.
Okay.
Because I write all the problems I do for the lectures and the homeworks, and so and I'm going to write the problems on the exam, so it's all in the same style. So yeah, I would say that definitely gives you enough practice. But if you want to get more, you can of course try to get the textbook and see what examples they have there. It definitely wouldn't hurt, but I definitely give you enough on the homeworks and the lectures to be prepared for this. Yeah. Okay. All right. Any other questions on the exam?
On the when assembling our global matrix, I remember, for example, in class, you would circle or boxing, with different colors like red, yada.
Yep. Mm-hmm.
Can we just do that on the actual exam, or do you want the actual numbers? I'm just saying that for timelines.
Yeah. So the matrix. So I will check the final matrix for the numbers with the boundary conditions, and so that one should have the numbers in it. But in between, if you want to save some time with just purely the assembly step, you just want to box it out without putting the numbers in. I'm okay with that.
Okay.
Yeah, because for that step, the assembly step, I'm mostly looking to see, are you putting the element matrices in the right place?
Okay.
And so I don't need the numbers for that, but I do want the numbers for the final matrix.
Okay.
Yeah, so that's actually a good strategy to kind of save some time. Yeah. So for people on Zoom, what the question was is that, when you're doing your direct stiffness method, right? So there's basically 4 steps. So there's element matrices. Element 2 is assembly, right? I don't know why the mouse is being so weird today. And 3 is the boundary conditions, right? And 4 is solve, but you're not going to solve these on the exam. So, so the question is, for the assembly step, do you need to write in the values for all the element matrices when you're plugging it into the global matrix? And I said that, I don't need to see the values on this step. So if you want to save a little bit of time and just leave the boxes there, just show me that you're going to put the element matrices in the right place. That's fine with me. But after you apply the boundary conditions, I do want to see all the values in the matrix at that point. And so you can save yourself a little bit of time where, if you do your assembly, you just box out or section out the matrix. Yeah, and that's perfectly fine with me. All right, any other questions on the exam? Okay. All right, so that was actually a much longer detour than I thought it was going to be, but that's okay. Okay. All right, so let's get into talking about MATLAB. Okay. All right, so the topic for today is, we're going to take basically our direct stiffness method. So, basically the same kind of methodology that we've been doing. So element stiffness matrices, assembly, boundary conditions, solve, and we're going to put it into a MATLAB program. Okay, so this is, I would say, kind of our first kind of big project, I guess you can say, in MATLAB, where we actually take our finite element technique and actually implement it in code. Okay. And just like it was commented early on today, where these problems, as soon as you add any kind of complexity to the problem, where you kind of add more than 3 or 4 elements, it gets very cumbersome and very kind of annoying to do. And that's because finite elements was never really designed to be a technique that you do by hand. Finite elements was always kind of designed from the beginning as a technique to use in a computer, because computers can actually do these calculations much faster than someone by hand. Okay. Okay. All right. So even though we're going to be writing in code, and I know that's I think for some people is a very intimidating kind of proposition. What you'll see is that the way we write the code is exactly the way that we do these problems by hand, right? So we're going to follow the exact same 4-step process. So we're going to compute the element stiffness matrices for every element in the stationary coordinates. We're going to assemble all the element stiffness matrices into the global system. We're going to apply boundary conditions, and then we're going to solve. Okay, it's just putting those instructions in a way that the computer will understand. Okay, because like I said at the end of class last time, that computer code is nothing more than just a list of instructions for a computer to do. Okay, and so you can teach a computer to do finite elements. You just have to write the code in the right way in order to teach them to do that. Okay. And so it's going to take some time. It's going to take some work to implement this code for the first time, right? So if you've kind of already looked at the starter code, yeah, you'll see that there's quite a lot there. But don't worry, we will kind of walk this through kind of step by step, and just kind of make sure that everyone kind of feels on the same page. Okay. So the problem that we're going to do is we're going to be implementing a frame code. So this is about as complex as it can be. For the types of problems that we've done so far. Okay, so we're going to do the really hard one together, and then for your homework, right? For your homework, I'm going to have you implement your own code, but not for frames, but for 2D trusses. Okay, so trusses are a little bit easier to work with because the element stiffness matrices are smaller, and they have less terms. And so the hope is that if we can do the frame one together in class, that you can take that same knowledge and that same approach and implement a 2D code that just does trusses. Okay. But first, let's kind of talk about this first. Okay. So the main thing, or kind of the main thing that you always kind of need to remember when you're writing this code is to always be aware of your variables and your data containers. Okay. So think about the way that you guys solve these problems by hand, right? So you're writing all these matrices down. Essentially, every time that you compute a matrix, you're kind of storing that as a variable that you're going to use later on. Okay. So let's say you compute the element stiffness matrix for element 1, right? You write it down on a piece of paper. You're going to use that information again later on, and you're going to refer to it, from your calculations before. Okay. The main difference is that when you're writing code, you have to be explicit in the step. So whenever you compute something, you have to save it to a variable so that you can, use it later. Okay. And we also need variables to keep track of basically every single numerical quantity for these elements. So things like the material properties, things like the geometric properties, things like the angle of rotation, right? Element stiffness matrix, global matrices, okay? So I think the beginning of the code might look a little bit intimidating, a little bit intense for people, but all we're doing essentially is we're making variables to store all of the numerical information that we need to run this code, okay? And then, I'm going to do my best just because I think once you start to get a lot of variables, it starts to get a little bit overwhelming. So I'm going to try to visualize these data containers as much as possible so that you kind of know exactly what's going on. Okay. Okay. And so, last point here too is that, we're going to be working off this starter code here. So I've already kind of, given you a start. And so we're not going to be writing this code from scratch, but, I'm just going to have you kind of fill in the blanks for this code here. Okay. For your truss code, you're going to write that on your own, but at least for this frame code, I think it helps to kind of start with the starter code. Okay. All right. So this is the problem that we're going to solve here. Okay. So this is just an example, but we're going to write the code in a way where you can actually use it to solve any frame problem at all. But I think it's helpful just for the sake of education, just for the sake of instruction just to have an example problem that we're working on throughout the class. Okay. So this is the frame problem that we did in class together. I believe it was maybe last Thursday or last Tuesday. I don't remember. But essentially we have a 3-element frame here. Okay. So we have 1 element, 2 element, 3 element. Okay. They're all arranged in kind of 90-degree angles from each other. And we have these forcing functions here. Okay. Okay, and so essentially, we're going to write our code to solve for the deformations for node 2 and node 3, because node 1 and node 4 are fixed to the ground. Okay. Okay. Bless you. All right, so let's go ahead and get started. Okay, so let's go ahead and jump into the code. Okay. Okay. All right, so you can see here that I've kind of sectioned off the code into different sections here. Okay. And I've written comments in terms of what you should be doing, okay? All right, so the first section of the code here is very simple. We need to define how many elements that we have in our system and how many nodes that we have, okay? Now, this is gonna change, right? So every time you apply this code to a new problem, you need to update these based on that geometry, okay? So actually, we need to put that note here. Change these for every problem.
Instead of changing them directly, could we also just make them user input variables?
I'm sorry, Lewis, the speakers on the computer are really soft. I can hear you talking, but I can't really hear you. Can you type up your question in the chat? Sorry. Let's see if I can raise the volume. All right, question. So instead of hard code changes, can we just use the input functions to make them more variable? Yeah, no, you can definitely do that too. So I wrote this starter code. So my age is kind of showing here. So I wrote this whole tutorial back in fall 2020. That was the first time I taught this class. It was over COVID. But yeah, so there's definitely a lot more slick things that you can do in MATLAB. So you can definitely do input functions where basically, every time you run the code, you're kind of forced to put those inputs. You can definitely do that. The only thing is that there's a lot of inputs that we need to do. So essentially, up until line 57 or 56, those are all inputs. And so if you want to put those as inputs to the script, you can definitely do that. It's just a lot to do. Yeah. Okay. All right. So first thing we're going to do is we're going to specify the number of elements and the number of nodes. So let's go back to our problem geometry here. Okay. So for this problem here, we can see that we have 3 elements and 4 nodes. Okay. And so let's go ahead and input that into the MATLAB code. Okay. So our number of elements is going to be 3, and the number of nodes is going to be 4. Right, very easy. So, these are variables that we're going to refer to very much later on, because these are going to determine, how many or how big our matrices are going to be, how many matrices we're going to have, and so on and so forth. Okay. Okay. All right. So the next thing that we're going to talk about here is the connectivity matrix. So this one I think is the first kind of piece of information that's quite new. Okay. So, if you recall, when we did these direct stiffness problems by hand, a big part of the process was, determining or keeping track of which nodes are connected to which elements, right? And so, let's go back to the diagram here, right? So if you were to do this problem by hand, right, and you were writing out all the element stiffness matrices, you would make note that element 1 here is connected to nodes 1 and 2. Element 2 is connected to nodes 2 and 3. Element 3 is connected to nodes 3 and 4, right? So we need to encode that information into MATLAB just so that we know what to do from there, okay? So the way this is typically done is through what's called a connectivity matrix, okay? Okay, so the connectivity matrix kind of looks like the following. And so it's, if you look at the code, you can see that we're defining a connectivity matrix as an empty matrix that has number of elements, number of rows, okay? So that means there's going to be 1 row in the connectivity matrix for every element in our geometry, okay? And the number of columns in this is going to be 2, okay? So the way it works is that, for any given element, right, we're going to go to that row in the connectivity matrix, right? So actually, let me draw out the connectivity matrix here. Okay, so for our particular problem, our connectivity matrix is going to have 3 rows because we have 3, 3 elements here. Okay, so this is going to be element 1, this is going to be element 2, and it's going to be element 3. Okay. Now the columns of the connectivity matrix, those are going to be the nodes that the element is connected to. So this is going to be node 1, and this is going to be node 2. Okay. So for instance, for element 1 here, right, the first node that element 1 is connected to, we're going to put that number here. And then the second node, we're going to put that number there. Okay. So I think I give you an example here. So element 2 in our geometry is connected to nodes 2 and 3. Okay. So that means in the second row of our connectivity matrix, right, the first node that element 2 is connected to is 2, and the second node that is connected to is 3. Okay. Okay. So I'm going to give you guys maybe 1 minute. Hopefully this is pretty straightforward. Why don't you go ahead and fill in just maybe just on a piece of paper, or if you want, you can just type it into the code already too. Go ahead and write in what the connectivity matrix would look like for node elements 1 and element 3. Okay, and let me actually bring up the problem figure just so you can look at it again as well. Okay. Okay, so we want I've already written in for you the connectivity for element 2. We know it's connected to nodes 2 and 3, but go ahead and fill it in for elements 1 and 3. Okay, so hopefully everyone kind of filled it in, right? So for element 1 here, right, element 1 is connected to nodes 1 and 2. So the first node here is going to be node 1, second node here is going to be node 2, okay? And element 3 here is connected to nodes 3 and 4. So, for this geometry, it's fairly basic. So we just have each element connected to each other. But that's what our connectivity matrix would look like, okay? Okay. And so if you go to the next slide, you can see that's exactly what the code, or that's exactly what our connectivity matrix should look like, right? So for element 1, it's going to be connected to nodes 1 and 2, element 2, 2 and 3, element 3, 3 and 4, okay? So go ahead and fill in, if you haven't done so already, go ahead and fill in the code here, and I'll do a 2 for the connectivity matrix here, all right? So you can see that, we're defining the connectivity matrix for 1, 1. This is row 1, column 1, that's going to be 1. Row 1, column 2, that's going to be 2. Okay. So connectivity matrix, second row, first column, that's going to be 2. For this one, second row, second column, that's going to be 3. Third row, first column is going to be 3. And then third row, second column is going to be 4. Okay. So the connectivity matrix is actually very, very good to understand because, that's something that is pretty much a staple in every finite element code, because you always need to store, we call this kind of the topology information, which is how the elements are connected to each other and how they're connected to the nodes. So that's very important for forming our linear system. That's very important for a lot of things that we do. Okay. All right. Any questions on the connectivity matrix? Okay. Okay. So you'll see where this comes in. So essentially, this is going to come in later on when we do the assembly. But we need to set the variables kind of first. Okay. Okay. Next, we have vectors that define the material and geometric properties for the elements. Okay. Now, there's no nice way to do this because every element can technically have different material properties, and so I've kind of defined it in kind of a very I would say primitive way here. So we're basically just hard coding the vectors in here. Okay, and you can see I've already kind of pre-populated this, and same with the connectivity too, right? I've kind of pre-populated this for 3 elements. But if we were to use this code for more elements, then you would just add additional entries here, okay? But essentially what we're doing is that, for every material property that we need for the element, so that whether that be the Young's modulus, the cross-sectional area, the moment of inertia, the length, right? Basically, we're defining vectors here that store those properties, okay? So the way this works is that, let me go ahead and go back to the figure here, right? We're basically going to write in, hard code, basically the Young's modulus and cross-sectional areas for every element that we have here, okay? Okay, all right, so for instance, element one has a Young's modulus of 30 times 10 to the 6 psi, has a cross-sectional area of 10 inch square, the length is 120 inches, its moment of inertia is 200, okay? So I'm gonna go ahead and input all that information into the code here. So the Young's modulus was 30 times 10 to the 6, so we're gonna do 30 E6. Cross-sectional area, what do we say? Cross-sectional area was 10 inch square, this is 10. Moment of inertia is 200. Okay. And then the length was 120. Okay. Okay, so I'll give you guys maybe a couple minutes just to fill that in, but just go ahead and fill in all the matrix properties here, or all the material and geometric properties here. So I'll leave this up and I'll give you guys a couple minutes to kind of do that. Actually, I'll do that. And by the way, if you have any questions, throughout this whole class is supposed to be kind of pretty informal and kind of interactive. So anytime, for Zoom, people just drop something in the chat. We can stop at any time and answer questions. If you're here in class, just raise your hand and I can come around to you guys too. Okay. All right. How's everyone doing? Everyone input all the material properties. So the last one we didn't put in is the angle here, right? So there's also a vector for the angles here, but I did want to kind of pause and talk about that in a bit. Okay. But did everyone put in all the other material properties for the Young's modulus, the length, moment of inertia, everything? Okay, good. Okay, so the last material property that we have here, I guess this is technically a geometric property, is the rotation angle. Okay. Now, we've already kind of talked about these angles before, so we kind of know how they are, right? So just going very quickly, we can look at the angles for each of these elements. So for element 1, right, the rotation angle is 90 degrees, okay? For element 2, we know that the rotation angle is 0. And then for element 3, just because node 3 is up here, right, we know that in order to rotate the element into that position, we have to rotate by 270 degrees. Okay, so that's why we kind of have these angles here. Okay. Now, when you're inputting angles in MATLAB, you have a choice, right? You can either input the angles in radians, or you can input it in degrees. Okay. Now, which one you choose, right? So first of all, be consistent. Don't swap back and forth between radians and degrees. But whichever one you choose, it's going to affect how you compute the cosine and sine later on. Okay. Because MATLAB actually has two different functions for computing sine and cosine. Okay. So there's traditional sine and cosine. I'm going to do sine of x and cosine of x. Okay. So traditional sine and cosine, this expects the angle or whatever input that you put into it to be in radians. Okay. And so that's what most people typically use, because when you compute sine or cosine, you typically just type sine or cosine. And so if you're going to do that in your code, then you have to put your angles here in radians. Okay. But there is a second sine or cosine, which is sine d. Okay. So there's a sine d and a cosine d. Okay. So these also compute sine and cosine, but this expects the input to be in degrees. Right, so either radians or degrees is fine. It's just whatever you feel most comfortable with. So I'm going to use degrees just because that's how I usually think of angles here. So theta 1 is going to be 90, theta 2 is going to be 0, and theta 3 is going to be 270. Okay, but I'm going to make a note so that whenever we compute sine or cosine, to use the degree version of sine or cosine. Okay, so either sine d or cosine d. Okay. But if you're going to use radians, then radians you can just use traditional sine and traditional cosine. Okay. Okay. Any questions on the angles and degrees? Okay. Good. All righty. Okay. Next are the boundary conditions. So this one is a little bit tricky. Okay. So we need to basically have a way, or we basically need a way to tell the code or to tell MATLAB where the boundary conditions are, as well as what the boundary condition values will be. Okay. Now there are lots of different ways to implement this. But I kind of chose a way that's kind of at least as consistent as I could be to kind of what we've done before. Okay. Because think about how we applied boundary conditions before, right? So after you apply, you generate the global matrix, right? When we applied the boundary conditions, the way we did it was that we first tried to look at which row of the matrix that we're going to be affecting. Okay. Right. So whether you have a Dirichlet boundary condition, a constraint, or a Neumann boundary condition, be a force or a moment, right? The first thing we always ask is, which row or which degree of freedom is this boundary condition going to affect? Okay. Okay. And so I've kind of encapsulated that information into how we apply the boundary conditions here. Okay. So if you look at how the boundary conditions are specified in the code, right, you'll see that I have a vector here called Dirichlet BC index. Okay. And so here, if you read the comment, you can see we're specifying the variable numbers for the Dirichlet boundary conditions. Okay. So in other words, we're basically specifying which rows in the global matrix we need to modify for the Dirichlet boundary conditions. Okay. Okay, so let's go back to our figure and then let's see which rows in the matrix that we need to set for this. Okay. So for Dirichlet boundary conditions, we have two, right? So we have a fixed support on node 1 and a fixed support on node 4. Okay. That means all of the degrees of freedom associated with node 1 and node 4 are going to be 0. Okay, and that's exactly kind of what it says right here. Right? Okay, so which degrees of freedom are associated with this? So for node 1 is very easy because node 1 is the first one that appears in our system. So that means d1y and d1x and theta 1 are all going to be equal to 0. Okay, and that consequently is rows 1, 2, and 3 in our matrix. Okay. Right. And then the same thing for node 4. So node 4, we're going to basically just wipe out the degrees of freedom with node 4. And that is the last 3 rows of the matrix. And so that's going to be, right? So if we have 4 nodes, that means we're going to have 12 degrees of freedom, right? So the last 3 are going to be 9. Sorry, I can't count. 10, 11, and 12. Okay. Okay. So let's specify these indices in our MATLAB code to say these are going to be the locations of our Dirichlet boundary conditions. Okay. Okay. So the way we do that is we go to this vector here. Okay. So this is going to specify the rows that we're going to apply our boundary conditions. That's going to be 1, 2, 3. Okay. So that's the first 3 rows, and the last 3 rows are rows 10, 11, and 12. Okay. So again, we're going to use this information later when we actually go to apply the boundary conditions, but we should at least define or specify where they're going to be. Okay. Same thing for the Neumann boundary conditions. And so we need to go back to our figure here. And we just see, which degrees of freedom our 2 forces are going to modify. Okay. So first thing you can see is that we have a horizontal force on node 2. Okay. So that means F 2x is going to be 10,000. Okay. And then we have a counterclockwise moment on node 3. So that means M3 is going to be 5,000. Okay. Okay. So now we need to ask ourselves, which rows in the matrix are going to correspond to F2x and which row in the matrix is going to correspond to M3. Okay. Okay. So if you ever get confused, and so for a simple problem like this, we can literally just kind of count it out. But for a more complex problem where it's you have maybe 8, 9, 10 nodes in the system, it becomes a little bit more difficult to find the exact rows. Okay. Okay. So if you ever get confused, right there, we have these 3 formulas here to kind of tell you, which degree of freedom corresponds to the x deformation of node I. Which degree of freedom corresponds to the y deformation of node I, and which degree of freedom corresponds to the theta degree of freedom for node I. Okay. Okay. So let's try to use these formulas and kind of see, right? Okay. So first thing we need to specify is going to be F2x, right? So that's going to be the x component of node 2. So we plug in, right? So we want the x component. So that's going to be the first entry here, first formula. Okay. So plug in I is equal to 2. Okay. That means that that degree of freedom is going to be 3 times 2 minus 1. So 2 minus 1 is 1 plus 1. Right. So we have 3 times 1 plus 1 is 4. Okay. So the first index for our Neumann boundary condition is going to be 4. Okay. So this Neu index is going to be 4. That's the first entry. Okay. And then our second entry here, okay, it's going to be the theta component of node 3. Okay. Right. And so theta component, we're going to use this formula here. Our I here is going to be 3. Okay. And then we're going to add 3 to that. Okay. All right. So we have 3 times 2, 3 minus 1, which is 2. So 3 times 2 is 6 plus 3. That's going to be 9. Okay. Okay. So we go back to our code. Right. And so the second index for our Neumann boundary condition here is 9. Okay, so that tells us that we're going to affect rows 4 and 9 with our Neumann boundary condition. Okay, and then the last thing we need to do before we move on to kind of the meat and potatoes of the code is specify the values here. Okay, now the values are given in the same ordering as your nodes up here, right? So first entry here is going to be the boundary condition on node 4. Okay, let's go back up to the figure here, or not node 4, excuse me, for row 4. Okay. So for that row, we can see that we're supplying a horizontal force of 10,000 pounds. Okay. So let's go ahead and write that into the Neu boundary condition value matrix here. So it's going to be 10,000. Okay. And then for row 9, which is the moment on node 3, we have a counterclockwise moment of 5,000. So we're going to enter 5,000 for the second entry right there. Okay. All right. Any questions on how we applied the boundary conditions? Good. All right. Okay, so now we actually get into the meat of the code. So this is where the code, we're done kind of specifying the properties. Now we can actually start to make the code here. Okay. So first thing we're going to do is we're going to make matrices for everything that we need in the problem, right? So first thing is we're going to need a global stiffness matrix. Okay, so that's going to be K global, a global forcing vector called F global. Bless you. And then a matrix here, a 3D matrix for the element stiffness matrices. Okay. Now, let's look at the size for each of these matrices. So first of all, you can see that we're invoking the zeros command. Okay. So the zeros command is telling us that we're creating empty matrices here. So everything's going to be filled with zeros. And then eventually we're going to add to these entries here. Okay. Okay. So that's the first thing. The second thing is to look at the structure of our element stiffness matrix, because we can see we have 3 indices here. Okay. So this means that our element stiffness matrix here is actually going to be 6 by 6 by the number of elements, which is 3. Okay. So this is actually a 3D matrix, which is like kind of trippy to think about, right? Because when you think of matrices, you think of just a 2-dimensional construct, right? But we have this structure here just so that we can save every element stiffness matrix that we're going to compute. Okay. Okay. All right. So the analogy that I have is something like this, right? So think of a file drawer, right? And so our data structure for the element stiffness matrix looks like the following, where each file we consider to be a separate element, and within each file we have the values for the element stiffness matrix. Okay. So basically what we're going to do is we're going to be computing the element stiffness matrix for every single element, and then, saving it into its file. Okay. 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 So let's go ahead and do just that. Okay. Okay. So let's go into the code here. Okay, so the next big section of the code starts on line 73. So the way you can view this is that we're going to have a loop here, and so this loop is going to visit every single element in the geometry, right? So this is kind of the same, I would say, convention that we talked about on Tuesday, right? So on Tuesday, remember that the best way is that if you have a list of things that you have to do, list of elements or list of entries to visit and do calculations, the best way to do that is with a loop. Okay. So you can see we've written this loop dynamically. So you can see that we're going to loop, we're going to repeat this loop by the number of elements, right? So however many elements we have, this loop is going to repeat that many times. Okay. Okay. And then first thing we're going to do in the loop is we're going to retrieve the geometric and material properties for that particular element. Okay. So recall, right? So back at the beginning of the code here, we defined these vectors to compute the material, or to store basically the material and geometric properties of each of the elements, right? So for every element, there's an entry in each of these vectors here. So E prop, A prop, I prop, L prop, theta prop, right? So all of these have the properties for that element, okay? So first thing we're going to do is we're going to retrieve those, right? Let's start here. Okay. So we have this variable E. E is equal to E prop at IL, right? So we're basically retrieving the element, or retrieving the properties for the first element here, IL. Okay. A is going to be A prop at IL. Okay. I is going to be I prop at IL, and L is going to be L prop at IL. Okay. So basically retrieving the material properties and storing them into these temporary variables that we're going to use in our calculation. Okay. Okay. The other thing that we're going to do is we're going to retrieve the angle for the element, okay, and then compute the sine and cosine. So you can see I've also created these temporary variables C and S. These are going to be the cosine and sine of this particular element. Okay. All right. And then from here we just have to compute the element stiffness matrices. Okay. Okay. So this is something that you're going to do. So I'm going to give you guys maybe 5-10 minutes to do this. But the way I've kind of set this up is that I'm basically having you compute each row individually, right? So this is the first row, this is the second row, third row, the fourth row, and the fifth row, and the sixth row, okay? So I've done the first row for you, right? So if you basically look, right, so let me actually bring up the element stiffness matrix for a frame here, okay? So I basically just input every entry into this first row for you already, okay? And you can kind of verify those calculations there, okay? Now, what I want you to do is I want you to write in the entries for the second, third, fourth, and fifth and sixth rows, okay? And keeping in mind that you can also make use of some of the symmetry that's involved in the matrix as well, just to save yourself some work. All right, question in the chat. Okay. Question. So do we have to add cosine d to make the angle? Yes, that's a great point. So yeah, so I wrote this code previously with radians, but since we are using degrees, we are going to change this to cosine d and sine d. Yeah, great observation. Thank you for picking that up. Okay. Okay, so why don't you guys go ahead and I'll give you guys maybe 5 minutes to kind of fill in the entries here. Okay. Right. If you want to make use of this, so you can go ahead and you can just write out the formula for every single entry in the matrix, all 36 of them, and that's perfectly fine. But if you want to make use of the symmetry, you can do that here. So this is basically the same thing that we did when we did these by hand, where every time we went to a new row, the first couple elements of the first couple entries in that row, we make use of the symmetry that was from the previous row. Okay, so that's kind of what I do here, and that's what I do here. Okay. And you can do that for rows 4, 5, and 6 as well. Okay. All right. Question in the chat. Let's see. Okay. Good. Okay. So I'll give you guys maybe 5-10 minutes. If you're kind of struggling with this, definitely raise your hand. I'll come around. This is kind of the first kind of big portion of the code that you guys are writing on your own. So don't be afraid to ask questions if you guys are getting confused. Okay. Let me bring up. Okay. I'll put this on the screen here just so that you don't have to, back in your notes and stuff. So this is all the entries for the element sequence matrix. Okay, all right. So I hear a lack of typing, so I think hopefully everyone has gotten to that. So so this is where we diverge, unfortunately, just because I didn't want to keep going back and forth with the code. I want to make sure you guys have this, but hopefully everyone was able to write in the element stiffness matrices. Okay. By the way, I do have a completed version of this code, so you don't feel like that this is going to be your only version of the code here. So I do have a completed version of this for you to reference. If anything, it will be good for you to check this code against the one that I will post eventually. But hopefully you guys are kind of following along. But I think it'll stick better if you kind of follow along dynamically rather than just wait for the solution to be posted. Okay. Okay. So last thing that's in this loop here, you're going to see is in line 133 and 134. Okay. So a couple of things actually happen in this line. So first thing that happens is, our frame matrix here is technically not just these elements in the middle here, but we have to multiply it by the quantity E divided by L. Okay. So we need to do that before we say that the element stiffness matrix is finalized. Okay. So you go back to our code here. We can say that we're multiplying E over L by this, okay? All right. All right. And then, let's see. Oh, actually, that's the last thing we're doing. I apologize. Yes, so that's the only thing we're doing in this line of code is we're multiplying E over L, okay? The other thing that, hopefully you guys have picked up on already is that, we are specifying the 6x6 element stiffness matrix here. We're doing it row by row, but notice that there is a third entry here that we're referencing. Okay. Remember, we're storing our element stiffness matrices here as kind of a three-dimensional matrix, where this third dimension here, this corresponds to the number of elements, right? So again, like the way to kind of read this is that, for every element, we're gonna have a 6x6 matrix, okay? And the number of, I would say kind of dimension, or the amount of depth that we have for this data structure depends on the number of elements that we have here, okay? And so as we compute each element stiffness matrix, we're basically storing it in that basically file cabinet, okay? Where this IEL corresponds to the loop index that we have up here, okay? Okay, all right, so that's the element stiffness matrix loop, okay? I'll go and catch up to you guys after, later on, okay? Okay, now comes the hard part here. So this I think is probably the most difficult part to do in MATLAB, just because, this was a part that we kind of did, we kind of just used our kind of intuition when we kind of did it by hand, and we did this in a very kind of visual way. So I think kind of, doing this in the computer and doing it in a way where you can kind of instruct the computer to do this, I think this is probably the most challenging portion of this code here. Okay, so now that we've kind of reached this part here where we've computed all the element stiffness matrices, we now need to assemble them into the global stiffness system. Okay, and to do that, we need quite a few pieces of information. So one thing we need is we need the element stiffness matrices, of course, but we also need to know which nodes that this element is connected to. Okay. Now, if you recall from early on in the code here, we defined this matrix called connectivity, okay? So this connectivity matrix, remember, this is our way of storing which nodes were connected to which element, okay? And so by going through this loop, right? So once again, we're looping over every element in the mesh, okay? For every element in our domain. And the first thing that we're retrieving is we're retrieving which node numbers are connected to that element, okay? So we're going to store that as N1. That's going to be the first node, and N2 is going to be the second node. Okay. Okay. Now, the node that is connected to and which row and column in the matrix that we start at, those are two different things, okay? So first thing we need to do is we need to compute kind of our starting points in the matrix of where we're going to start assembling, okay? So for instance, let me kind of draw out the situation with a matrix here, okay? Okay, so let's say that we want to assemble the contributions from element 2, right? So we know element 2 is connected to nodes 2 and 3, right? And so we need to find out, which row and column in the matrix that we need to kind of draw this matrix into, okay? Okay, so if we draw the matrix here, we know the first 3 rows in the matrix are going to correspond to node 1. So this would be D1x, D1y, and theta 1, okay? D1x, D1y, theta 1, okay? So node 2's contributions actually don't even start until row 4, right? So we have D2x, D2x, right? Right, and so if we're looking for the location where we're going to input the element stiffness matrix for element 2, we're actually going to start at row 4, right? And then go from there, right? So these indices, these IND1, these IND2, these tell you, which row in the matrix that we need to start our contribution, adding our contributions to, okay? Now we're in luck, right? Because if you know the starting point for each of those nodes or for each of the entries, then every entry after that is going to be basically the next 3 rows, the next 3 columns, okay? And so we only just need to know where our starting point is, right? And so our starting point is basically just going to be the x component of that, particular node in the global system. Okay. 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 So I'm going to refer back to some formulas that we talked about earlier in the class, right? Okay. So if you recall these formulas here that we had for the boundary conditions, right? We use these formulas to tell us, which rows in the matrix correspond to which degrees of freedom, right? So for a given node I, the x component of that degree of freedom is 3 times I minus 1 plus 1, where I is the node number that we're referring to, okay? Okay, so if we go back to that section of the code there, okay? So if we're looking for the x component for that particular node, we're going to plug in for that formula there. So we have 3 times n1 minus 1 plus 1, okay? Where n1, that's the node number for one of the nodes that this element is connected to, okay? So there's quite a few layers of kind of, things that are going on here. So, first thing, let me just kind of summarize. So first thing, right? First thing we need to do is we need to retrieve the node numbers that this element is connected to, okay? Then we need to translate those node numbers into the appropriate rows in the matrix that we're going to be acting on, okay? And that's what these lines do. Okay, so first thing I want you to do is I want you to compute the starting index or the starting row for node 2. Okay. So you guys maybe like 30 seconds to kind of do that. It's very easy. Okay. All right, so, if you're just kind of following the same pattern from node 1, then the starting index for this would be 1 plus 3 times n2 minus 1, okay? All right. Okay, now get to the hard part. So now that we know where to start, how do we even go about kind of inserting those entries in the matrix, okay? Okay, so I have this slide here to hopefully kind of help you out, right? So we're going to be, eventually we're going to be basically adding in all 36 entries in this matrix, okay? But the way to kind of do that is, I've kind of broken it up here into kind of 4 different submatrices, okay? Now the submatrices are corresponding to, different combinations of degrees of freedom for each given node, okay? Remember, like I said, basically, all the degrees of freedom for one node are always kind of packaged together. So, everything in these first 3 columns, they're going to be the degrees of freedom for node 1. Everything in the first 3 rows is the degrees of freedom for node 1, okay? And so that means that these submatrices here, they're going to go in together. in the matrix, right? So we may have situations where, maybe these submatrices are separated, right? So we have a global stiffness system, okay? Maybe we're inserting the entries for this matrix. Maybe, one entry is going to go here, another entry is going to go here, another entry here, another entry here, okay? So I know we didn't do too many of these with frames, but, think back to when we did 2D trusses, right? We saw this pattern quite a bit where we had kind of our 4x4 matrix kind of split up into 4 different sections in the matrix, okay? So it's the same thing for frames, except, each submatrix here is 3x3, okay? Okay. So we're gonna add those entries into the matrix in those kind of batches of 3x3. Okay. All right. So let's go back to the code here. Okay. So I've done kind of the upper left kind of entry for you here. Okay. Okay. So you can see here that we're adding entries to K global. Okay. You notice first of all that we're using our update notation, so we're not overriding the entries there. We're adding to it. Okay. So we say K global at IND1, IND1 is equal to K global at IND1, IND1 plus our element stiffness matrix at 1, 1. Okay. All right. So basically what we're saying is that the top left entry in our element stiffness matrix here, okay, is going to be inserted into the proper location into the global stiffness system. Okay. Same thing for the second one, third one, this one, and this one. Okay. Okay. So for this portion here, I would definitely look and see how I did this for you here, right? So this is basically the template, okay? So this is the top left part of the matrix, okay? Oh, also, by the way, we retrieved the element stiffness matrix for this element just to make things a little bit easier for us to work with, okay? So I said that KE is the element stiffness matrix for this element here. So I basically said, give me every row and every column for this, element here, okay? So now this KE is a 6x6 matrix. Okay. And so we're basically finding a home for all 36 entries in that matrix here. Okay. Okay. All right. So that's how we did it for the first entry here. So that one's pretty straightforward, right? So basically the X component of the first node goes into the proper place here. Okay. Now look and see what we did when we moved columns here. So everything is kind of based off the starting point of IND1, right? So if we move over a column, right, so we go to the first row or the row corresponding to IND1, and we go to the column right next to it. So, we go just through IND1 plus 1, right? That entry is going to correspond to KE at 1, 2. Okay, so that's basically this entry in the matrix right here, right? That's going to go into IND1 plus 1 in the column here. Okay. Same thing for the third column here. Okay. Okay, so definitely, take your time, look at this, right? See how this is implemented. And I've already even started the second block here. So the top right 3x3. Okay. Now, for the rest of the class today, I want you guys to work on kind of inputting everything for the to-dos here. Okay. Now, this is probably the most confusing part of the code here. So, don't be afraid, try something, make mistakes, call me over and ask questions. But we're going to work on this for the rest of class today. We'll pick this up again on Tuesday and kind of talk about it again. Because again, I think this is probably the most difficult part. After this, we have to apply the boundary conditions, but these ones are actually fairly simple, and the Neumann boundary conditions, and then the solution here. Okay. Why don't you guys keep working on this? I'll come around. Go ahead and raise your hand if you have questions. If you have questions on Zoom, once again, just leave a comment in the chat. I'll come around. But this is kind of it, or this is kind of where I want to stop for class today. Okay. But we do have the class for the last 5 minutes, so definitely make use of that. Raise your hand, ask questions, just so that you can kind of think about it while we're over the weekend. Okay. Okay. All right. So I will go ahead and make my round. So if you have questions, raise your hand. If not, then yeah, I guess see you guys next week. All right, so it's 6:45, and so that's technically the end of lecture. So I'll stick around until Dr. Weiss comes and kicks us out. But thank you guys for coming today. Hope you guys have a good weekend. So again, we'll pick this up on Tuesday. I do want to spend a bit, so I kind of rushed a little bit at the end with the assembly. So I think what we'll start with on Tuesday, I'll start with the iPad. Just kind of illustrate this concept a little bit more, because I think it's important of the assembly. And this is definitely going to come back. When we do kind of our more complex finite element codes later. So this is definitely a good point to know. And we'll finish up the code from there. All right, so thank you guys. I hope you guys have a good weekend, and I will see you guys next week.
Yeah. Oh, the answers. No.
I was just wondering if I could just read up with you a little bit and go over the steps step by step. That's like I'm not fully getting it.
The ANSYS activity?
Yes.
Let's talk right now. So I do have to go pick up my son.
I haven't looked at
I do have like
Are
5
they
minutes.
conceptual or do they have to do with program?
You're in the program. There is one conceptual. So it'll be like, oh, show me, like, change
Yeah.
or stuff like that. The first 3 work.
Oh, you've been running this on your PC? Okay.
This,
Okay.
yeah.
Yeah. It's a big program.
Wait, I
Talking about, I think 40 gigs.
So this one is.
don't think it's getting worse.
Change the force.
Sorry, I already had my, that's why I had to.
Okay. So I mean, what we're going to do. I would say. And then.
Can you just ask them right now?
Yes.
Because it's due on. Yeah. You know, stay here because
Yeah, or if you do the other aspects.
Okay. One after the engineering, like, workstation. Okay.
Are you on Windows 11? Yeah. Yeah. It's because the PC at home I have is Windows 10, but I don't know if I have the hard. So I don't know if ANSYS will still be able to install Windows 10 because you know how Windows 10 is deprecated. And then I also, since I built that PC like 6 years ago, something like that, I don't know if it has the hardware to go into it. Because I think the motherboard has got like some specific chip or something like that.
Yeah, it's be.
Yeah, so for instance, I said
Well, no.
So the document.
So I bought when I bought it, I bought a Ryzen, I think a 9. So, sorry, a Ryzen, whatever Ryzen's equivalent to a 9 whatever it is. So I bought that one, that.
Yep.
Had some questions about that, the homework.
Sure.
The activity.
Mhm.